Hello, welcome to my channel. My name is Ange, and in this video we're going to continue from where we stopped. Okay, we're dealing with complex numbers. Good. So we're going to look at properties of complex numbers, but not just that. In the properties we're going to look at addition of complex numbers. All right, so we're going to talk about when we can add two complex numbers to get out two or more, and so on and so forth. Subtraction, multiplication, and probably division. Maybe that will be in our next video because division needs a little more thing. But okay, let's just see where we stopped. But we'll definitely finish up. All right, maybe not in this video. So properties of complex numbers. So let me just start off by saying if you are given two complex numbers. So if given two complex numbers, this and that, where the A, B, C, and D are real numbers, and then the I here in these two represents square root of -1, right? The following properties hold. So if you have the following, so we say the following. So I would like to use FF to represent the following properties, right? Hold. So the following properties hold. So the first one I'd like to look at is equality of complex numbers. So the equality property. When can we say two complex numbers are equal? Well, I'd really like to look at this using a diagram. A diagram, a representation of complex number using diagram to explain when we say two complex numbers are equal. But it's also easier this way. Now, two complex numbers are said to be equal if their real parts are the same and their imaginary parts are the same. That's not necessarily the same with the real part. So this is it. Two complex numbers, let's say A plus BI, is the same thing, that is A plus BI is the same thing as C plus DI. Those are the two complex numbers given, okay? And this is true if and only if. So I'm going to put it this way, using piecewise function. This means if and only if, all right? The real part of the first complex number, A plus BI, is the same thing as the real part of the second complex number, C plus DI. Good. And also, if the imaginary part of the first real number, A plus BI, is the same thing as the imaginary part of the second complex number, all right, C plus DI. When these two properties or when these two conditions hold, then the equality of the two complex numbers hold. Good. So what do we mean by the real part of a second complex number? Of course, we discussed earlier that the term that is independent of the I sign, right? That's the A here is the real part of this complex number. The C here is the real part of this second complex number. So when A and C are the same, then and also when B and D are the same, and also when B and D are the same, then we can say that these two complex numbers are equal, right? Good. That's what we mean by imaginary part. The imaginary part is B, the imaginary part is D. If these two hold, if these conditions hold, then, but if one of them hold, then the two complex numbers are not the same, all right? Good. Okay, so let's look at the second one. Or maybe I should give an example. There is no point for example because it's going to be kind of trivial. You know, okay, let's do a non-example. I think a non-example is better. So as a non-example, so let's say we are given a complex number. Let's say 2 plus I, right? So we have 2 plus I, and we are given another complex number. Let's say 2 minus I. Good. So the question now is, are these two complex numbers equal? Right? So you notice that this is the real part of the first complex number. This is the real part of the first complex number. They're the same. 2 is equal to 2. Of course, that's impressive, right? So we're looking happy. But look at this. The imaginary part of this complex number is what? It's +1, right? Then the imaginary part of this is -1. So +1 and -1 are two different real numbers. In other words, these two complex numbers are not the same. So maybe you can have a really sad face, right? Oh, yeah, they're not the same. So they will be the same if 2 is 2, and then maybe if this is 1, this is also +1. Okay, great. So let's look at another property. It's not really, it's going to be more like an arithmetic operation of complex numbers, but I'm going to tell you when the addition is possible, all right? So addition of complex numbers. So talking about adding two complex numbers together, when we add two complex numbers, we add the real part to the real part and the imaginary part to the imaginary part. So to compute this sum, a plus bi, that's the first complex number, added to the second complex number, c plus di. Okay, we, of course, like I said, we add a and b. That is, we compute a plus b. Also, we add that's c. We add a and c. Right? Sorry for that. That's okay. Also, we add b, I, and di. So that will be, we'll have bi plus di. Of course, that just b plus d net I taken. So what that means is we'll add the real parts together, and then we add the imaginary parts together. Just the same way we treat sorts, right? Good. So you know that complex number, the idea represents square root of -1, which is the square root term. Same thing with the sort, where the number you are taking the square root of is not a perfect square. Good. So you tend to add the this to that, and then the imaginary part to the imaginary part. All right. So if you're given an example, let's say you want to add, just as an example, of course, I think it's quite clear. Let's see. Okay. So you want to add 2 plus 3i, 2, 4 minus I. Good. So you notice that the real part here is 2, irrespective of the arrangement. It's not always the first number, that the first term that will always be the real part. Is the part independent of the I. So the real part here is 2, the real part here is 4. So the sum will give us 2 plus 4, right? So we'll add 2 and 4 together. Then we will now add this 3i to -1i. So we have 3i plus, right, -1i. But you notice that 2 plus 4 will be 6. And then we add it with 3i plus and minus, of course, that's minus. Then 3i minus I, that's 2i, right? This gives us a negative here. This minus that will be 2i. Good. So that is what we get as a result after adding these two complex numbers together. So you just add the real parts of this one to the real part of the other one. You can still add more than 2 complex numbers. If we are to add, let's say 10 complex numbers, right? Pick the real part of each of them, add the real parts together, then pick the imaginary part of each of them, add them together. It's more like saying add the like terms. Okay, it's as easy as that. Okay, so and subtraction of complex numbers follows similarly as that. So just subtraction, you have this, then and then that and that. So maybe you can do that. You can just do the work and then put your answer in the comment section. So it's a good work for you. If you, that's just like a work. 4 minus 2i, you want to subtract this other complex number from that. Let's say we have 3 plus 5i. Good. So this is a subtraction. It works similarly when you want to subtract two complex numbers. Subtract the real part of the second from the real part of the first, and then subtract the complex part of the second from, the imaginary part of the second from the imaginary part of the first. And of course, when you take the imaginary part, you always endeavor to have eyes with them, right? Not when you to find the imaginary part, but when you to compute the subtraction. But the imaginary part of the complex number is the number that stands with the I, not together with it. So the imaginary part of a plus bi is b, right? Not bi. Good. Okay, let me clean this part so that we see how we can compute the product of two complex numbers. Okay, so taking the product of two complex numbers is not going to be as straightforward as the addition and subtraction, where we just have to say, okay, add the real part of this one to the real part of that, right? In this case, it's not going to be multiply the real part of this to that. Sorry about that. So this is what we do. So So we're given the two complex numbers here, a plus bi and that. So let's put them out, and we want to compute the product, all right, of the two. Then we have this other one. We want to multiply it with this other complex number, c plus di. Okay, so this times that. Of course, when you to multiply two brackets, you know how to distribute, right? So you just use this first term, you multiply everything in the second bracket. So you use each term of the first bracket to multiply everything in the second bracket, and then you use the second term as well, that's each term in the first bracket to multiply, or you can do it vice versa. Good, because it's multiplication, the operation is commutative. So we multiply a with c, and then we add the result with the product a with di. So that will be a times c, all right, this is times here. Then we have a times di, so we add it with a times di. Okay, good. So we also multiply bi times c, that will be plus bi times c, all right. Yeah, I'm going to rearrange, no problem. Then we have bi times di, so we add it with bi times, permit me to use the times here, di. Good. Okay, so this is just ac, that's nice. Then we have adi. Good. Now bic, of course, since multiplication is commutative, I'm just going to put bci, all right, that's b times c times I, where the I is square root of -1. Good. Now we observe this bi times di. Again, I'm going to rearrange this a little bit. This is going to be b times d, okay, given that multiplication is commutative. Then the remaining I and I, which we have to multiply. So we have I times I. Of course, those two things are the same. I times I is going to be I squared. But you can take note that I is the square root of -1. So when you square the square root of -1, in fact, you have -1. Right? So we take the square of the square root, which is the square and the square root, to cancel each other out. And then the product will give us -1. So in fact, that's a very nice property to take note of, that when you have the square of the unit imaginary number I, the result is just going to be -1. And it's a really interesting stuff, you know, to square a number and then you get a negative result, because we know that when we square a number we should get a non-negative result. Well, that is for real numbers, right? And here we are dealing with complex numbers, so yeah, it shouldn't be surprising. Good. In fact, the way we started by seeing that x squared could give us -4 if x was positive or -2i, so that works. Great. Now you know that we usually like to, in the form of a complex number, we like to have the real part plus the imaginary part, right? There's the real part is a part that does not have, that is not with the sort of, okay, with the I, that is with the square root of -1. So it's the part independent of, so we have AC here. This has an I, this has an I, but this does not, and that's because we had to evaluate I square, all right? So in that case, we're going to put down AC here. Then you notice BD times -1 is negative BD, so we have negative BD, all right? Negative BD. Good. Then these two here, they both have an I, so we're going to factor out the I. When we do that, we're going to have AD plus BC. Okay, then the I is being factored. So we have it out here. They both have an I. And in fact, this is very nice because this is the real part, this is the imaginary part, and the whole thing is a real number. So that is how to multiply two real numbers, by distributing, using one bracket to multiply every term in the other. Okay, so we can do an example. So let's see, I say 2 plus 3i. So let's do an example real quick. So you have 2 plus 3i. You want to multiply it by 4 minus an i. Good. So you want to take the product of these two complex numbers as a particular example. Okay. So you notice here, it's just easy. Well, you can use the main result. Given that a is 2, b is 3, and so on. Then we just substitute into this and we simplify and get it done, right? But we can still distribute. So why not? So let's see, we would make use of the 2 multiplied with 4, and then that same 2 multiplies with -i. Then we use 3i to multiply with 4, then that same 3i to multiply with the other part. So from here we're going to have 2 times 4, okay? So let me just put it out, 2 times 4. In fact, there's no point. 2 times 4 is 8. Then you multiply 2 with negative I, that's negative 2I, right? Good. Then we compute this and that, that's 12I. And then we have 3I times negative 3I times negative I. So I'm going to let's take it bit by bit, okay, in that part. So we have 3I, we multiply it by negative I. Good. Okay, so of course 8 is here. Now these two terms both have the I. Negative 2I plus 12I, of course that's positive 10I, right? So let me just put it down here, positive 10I. Good. Now let's simplify this and see what we have. This right here is 3I times negative I. Of course we know that I times I on its own is going to be negative 1, right? So we have positive 3I times negative I, that will be negative 3, then I times I, which is I squared. So this 3 times negative 1, that is the coefficient of that I is the negative 3, then the I and itself will give us 1 when multiplied. Good. So you notice that from here, well, since I on its own is negative 1, since I squared is negative 1, negative 3 times negative 1 will give us positive 3. So we're going to have here to be 8. Negative 3 times negative 1 is positive 3, right? Then we add 10I to that. And of course we are done. This is just 11 plus 10I. So you try to add like terms by adding terms with the I together, then the other ones together. And you notice that you can't add these two terms together, right? And that's the result. Okay, that's nice, isn't it? Good. So let's do something on multiplication as well. So we have the fourth one here, which is multiplication, not multiplication, division of two complex numbers, which were given to be this and that. So let's say we want to use this as a denominator and this as a numerator, given that this is not 0, okay? When is a complex number 0, a complex number is said to be the 0 complex number if C, which is the real part, is 0, and D, which is the imaginary part, is 0. So when the real part and the imaginary part are both 0, then such a complex number is said to be the 0 complex number. So to compute a fraction or a division where the denominator is the 0 complex number, the result will not be defined because we don't like to divide by 0, right? Not that we don't like to, but we cannot divide by 0. So C plus DI, I'm going to say where C and D, where C is not 0 and D is not 0 as well, right? So where the two of them are not 0, the real and imaginary part of the denominator. Okay, great. Now, just like we have in sorts, to take the ratio of two sorts, we make sure that we evaluate the irrational number in the denominator. That is, we try to multiply the numerator and denominator by a thing to make the denominator to be more rational or to become rational. Yeah, that is by rationalizing the denominator of a sordic expression, or a sort of a sort. Yeah. So given that this behaves that way, we are going to do the similar thing. And to rationalize the denominator of a given sort, we multiply the numerator and denominator by the conjugate of the denominator. So the conjugate of a sort has this form. So if you have a sort of the form, let me just put it out here. Let's say A plus B root C. Okay, the conjugate is A minus B root C. So you change the sign of the coefficient of that sort, right? Change it from whatever it was to the opposite. Positive changes to negative. If it was negative, changes to positive. That will become the conjugate. So the complex conjugate of this complex number is going to have the same form, but in this case we are going to change the sign here from plus di to minus di, right? Good. So that's the thing we're going to use. So you keep in mind, just work similarly, the same way just similar to the same thing we do in sorts. So to divide these two complex numbers, given that this denominator is not the 0 complex number, this is what we're going to compute. That is the fifth sorry. So we're going to compute, we're going to say a plus bi divided by c plus di. Of course, now we're going to do multiplication by 1 using the conjugate of the denominator. This is the same thing as we're going to have a plus bi, okay, we divide it by c plus di. But given that the conjugate of the denominator is c minus di, so we would say let's multiply numerator and denominator by the conjugate of the denominator, which is c minus di, and then c minus di. Good. So if we multiply the numerator and denominator by this will help us to sort of rationalize. It's not really rationalize, but to we do make this so that we can get rid of the complex term in the denominator. Yeah, the reason is we don't really like to be at in the bottom. Black pen, red pen. We don't like the I here to be in the denominator. That's the essence of evaluating this. Good. So we have this to be, well, this times that, okay, which we've done already, the multiplication of two complex numbers. When you multiply these terms together, a times c, we're going to have ac there. We can just do this in our head. Then bi times negative di. Of course, this negative, this positive, the result will be negative there. Okay, let me just take it bit by bit. Bd. Then I times I will give us a negative 1. So you keep that in mind. So the positive times negative is the negative. B times d is the bd. Then I times I is the negative 1. Alright? Then we have multiplied a with negative di. That will be negative adi. And then we also multiply bi with c. That will be positive bci. Good. Then the denominator will do a similar thing. Alright? Just expand c times c. Of course, that's c squared. Then we're going to have c times negative di times negative di. Negative times positive times negative, that's negative. D times d, of course, that's d squared. And then we have I times I, which is negative 1. Good. Then we have to multiply c with this part, which is negative cdi. Then positive di times c, that will be positive cdi. Okay. Good. Now you notice that this is negative cdi and this positive cdi. So they are both equal and opposite in sign, right? So in fact, that would just give us 0. So in this case, we're going to have, well, as you can see, we've eliminated the I in the denominator, and that's the essence. That was the reason we multiplied this by that, this and that by the conjugate of the denominator. Good. So simplifying this, what is negative bd times negative 1? That's positive bd. So we have ac plus bd. The two terms here have an I, alright, so we can factor out the I, and then you keep in mind that this first term has a negative. So this is what I'm going to do. We factor this out, and we also factor out this I. That's the numerator, so this is the denominator. When we factor out the negative sign from the first term, there will be no negative, and then we factored out the I as well, so we only have AD left, right? Now for the second term, it was positive. Okay, we divide it by a negative sign, that is by factoring out the negative sign, so it now becomes negative. Then BC, we factored out the I. Good. The denominator, this and that have eliminated each other. We'll be left with c squared. Now this is negative d squared times negative 1. That'll be positive d squared. Alright, so we add d squared to that. Good. So here, this is very nice, but we can make this better. Remember, we like to put a complex number in a form where we have the real part plus the imaginary part. Alright, that is imaginary part, then the I. So this is a real number, and if you split the fraction, split this fraction, we're going to see that. So this is going to be this, that will be a c plus bd. We divide it by this denominator, right? That is c squared plus d squared. And then we also take this one, divided by the same denominator. And I would like to have a positive out here instead of a negative. So this is what I'm going to do. We'll just put this way, bc minus ad. Alright? And then we have divided by c squared plus d squared, and then we put the I out here.